We shall start our discussion today on the applied thermodynamics. In particular, the topic of our today's discussion is the exergy analysis of steam turbine, and then finally, we shall try to solve two problems from the steam power cycles. Okay. So, now before I go to discuss about the exergy analysis of the steam turbine, in fact, I am thinking that instead of having only the exergy analysis of the steam turbine, it would be wise to have the exergy analysis of the power steam power plant itself or the power cycle itself. Now, if we try to recall that the component of the steam power cycle, be it ideal Rankine cycle, reheat Rankine cycle, regenerative cycle. So, mostly we have seen that there are so this is the diagram schematic. We have discussed this diagram many times. So, now question is, why do we need to go for the exergy analysis? Rather, I will be writing the second law analysis of the power cycle. Steam power. Okay. Now, you have studied about first law of thermodynamics, second law of thermodynamics in your thermodynamics course, and I am very much sure you know the necessity of the second law of thermodynamics. So, first law of thermodynamics talks about the conservation of energy. It does not provide the direction of any energy transfer. Second law on the other hand came only to address the limitations of the first law of thermodynamics. So, the limitation of first law of thermodynamics is that it talks about the conservation of energy, but it does not provide the direction of energy transfer. So, second law can provide that. Not only that, second law of thermodynamics provides the concept of entropy. So, now when the entropy is, you have studied about this particular property, now thermodynamic property. Now, when there is entropy, which is nothing but the source of entropy generation is essentially due to the irreversibilities of the processes, and when there is irreversibility, entropy will generate, and because of this generation of entropy, the expected output from any particular device, if a few devices constitute together to form this cycle, so the output from the cycle will be reduced, right. So, now question is, second law analysis is important in the context of steam power cycle, essentially to understand the availability of the rather work output. So, basically what you can see from the schematic depiction is that though there will be many other small components, but at least from here we can see boiler is there, turbine is there, condenser and pump. Now, the efficiency or the overall efficiency of the plant will be eventually determined by the efficiency of the individual component. So, these 4 components constitute the cycle, all the processes to operate in a cycle. Now, as I told you that if you do not have this condenser, it is very difficult to have the processes in a cyclic manner. So, and that too you have understood from the second law, that second law puts a restriction that it is not possible to have a cyclic process when it is working with a single temperature thermal reservoir. So, now when there are 4 different components as such we can understand from this block diagram that these are the major components. Irreversibility associated with the process which is occurring in a particular component will, if we sum up all those irreversibilities, that will be the total irreversibilities of the cycle. And when there is irreversibilities, the expected work output from the cycle will not be equal to the will not be there, rather the what we can expect, that the maximum work that we can expect from the system will not be there. Instead, we will be getting little less amount of work, and that is because of this irreversibilities. So, now from the second law of thermodynamics, since the concept of irreversible entropy is there, unlike entropy there is another important property that is called exergy. What do you mean by exergy? So, this is basically potential to do work of a system in a given environment. See, I mean this is basically, why I am telling given environment, because this is steam power cycle, you can understand you are supplying heat into the boiler, rather to the water which is passing through the boiler by burning any fuel, be it coal, be it diesel. Now, also see the performance of the condenser essentially will depend on the temperature of the water or coolant which will be supplied to reduce the temperature of steam. So, that also will depend on the environment in which this power plant is situated or power plant is installed. So, this is nothing but work potential of a system in a given environment. So, I am writing this is nothing but the work potential of a system in a given environment. Okay. Say this is the, if I talk about turbine. So, when steam is entering into the turbine and finally after doing some work it is leaving from the turbine. So, if we consider the working substance, I mean if we now focus on the working substance, that is steam, so the state of that steam is getting changed as it passes through the turbine. So, when steam is passing through the turbine, the thermodynamic state is getting changed. At the cost of that change of the thermodynamic state, we are getting work output. So, we can extract work. So, question is, this, I mean we are getting work output. So, work delivered as the, so you can see that if you consider this is a if you let us say if I take red color, and if we consider that this is the control volume system, because this is flow process, right. So, this is not the control mass system, because we are having inlet and outlet. So, there is a control volume system, that is flow system. So, now if we focus our attention on this control volume system, we can understand the system, the working substance of the system is changing, I mean state of the system is getting changed from the inlet to the outlet, and that is why we are getting work. So, work delivered by the system, I mean if you consider this is the control volume system. So, work delivered as the state changes from inlet to outlet through a reversible process, because again we are telling that all the processes, I mean which are there in this particular cycle, say constant pressure heat addition inside the boiler, isentropic expansion when steam is passing through the turbine, constant pressure heat rejection in the condenser, and finally the work input, that is reversible adiabatic. Okay. Now, all these processes are assumed to be internally reversible, but we cannot promise to have externally reversible all the all the processes to have the external reversibility. So, we can assume that all the processes are internally reversible, but at the same time we cannot promise that all the processes will be having external reversibility, because we will be having heat transfer to the working substance due to finite temperature difference. If we are unable to maintain the finite temperature difference, heat transfer so efficient, heat transfer will not be efficient. So, as long as efficient heat transfer is ensured, external irreversibility will be there. Similarly, I mean here really, I mean though we are providing kind of insulation on the turbine blade at the turbine casing, but some amount of heat loss will be there. Not only that, steam is passing through the turbine blade, as you have discussed, that steam will impinge. So, frictional effect will be there. Also here that today in a last class we have discussed about that because of the heat transfer due to finite temperature difference, external irreversibility will be there. So, though external, I mean internally reversible all the processes, we cannot ensure that the processes will be externally reversible. So, what I am telling, if we assume this is the control volume system, work delivered as the changed as the thermodynamic state changes from state 3 to state 4 and the processes is occurring reversibly, then the work output, I mean that work delivered and will be the exergy. So, basically there is a control volume system. So, work delivered by the work delivered as the state of the system changes from state 3 to state 4 reversibly, and when the system, that is control volume system, is coming to the dead state. So, basically if we allow the control, if you allow steam to expand reversibly and the work that will be delivered, if I allow system to change its states from 3 following a reversible process up to the dead state, right. So, that is the work and that is nothing but that is the measure of exergy. So, basically it is work potential of the system in a given environment, and in a way I can tell you that maximum work that is obtainable from the system when the system is coming into the dead state, equilibrium with the surroundings. So, that is nothing but exergy. Okay. So, though you have learned on this particular topic in a greater detail during your thermodynamics course, but just to have a brief recapitulation I have discussed this part. So, now question is, that we know second law efficiency. What is second law efficiency? Second law efficiency is nothing but, see, when we are getting work output. So, the minimum reversible work, I mean that is obtainable, minimum work obtainable from the system or the actual work obtainable from the system to the reversible work. So, if I try to find out, even if we focus on this particular part, maximum or reversible work that is obtainable from the system is not equal to the actual work that we are getting, and that is because of the thermodynamic irreversibilities. Okay. So, fluid friction will be there, mechanical losses will be there. Considering all these losses, the actual work obtained from the system is not equal to the reversible work that is obtainable from the system, and the ratio of these two work is nothing but the second law efficiency. Okay. So, now question is, as you have discussed about that because of the friction mechanical losses will not be able to get the maximum obtainable work, and that is the exergy destruction will be there, right. So, exergy is the basically work potential of the system in a given environment, but because of the thermodynamic irreversibilities there will be exergy destruction, right. So, why exergy destruction is there? Because of the thermodynamic irreversibilities. Which are the factors producing thermodynamic irreversibilities? Friction, mechanical losses, heat transfer due to finite temperature difference. So, these factors leads to entropy generation and simultaneously also leads to exergy destruction. So, the factors which leads to the entropy generation also lead to the exergy destruction, right. So, the friction, heat transfer due to finite temperature difference here in the condenser, heat transfer due to finite temperature difference in the boiler, all these factors lead to the entropy generation. That means they are inviting irreversibilities into the system. So, now these factors, so basically you can understand these factors lead to the irreversibility generation and also lead to the exergy destruction. So, exergy destruction is nothing but due to the irreversibility of the system, and which you know that in from your thermodynamics knowledge this is nothing but the entropy generation. Okay. So, higher the entropy generation, which is nothing but the higher degree of irreversibilities, higher will be exergy destruction. Okay. So, higher the irreversibility of the system, higher will be entropy generation, and which in turn will lead to the higher exergy destruction. So, if we try to write in a what is exergy destruction, I am writing in the rate form. So, this is nothing but T naught into S dot gen, right. So, this is known as exergy destruction. Okay. See, for any, I mean, since I am, as I told you that we will be focusing on the exergy destruction of the cycle itself. I mean, you can calculate exergy destruction of the turbine, you also can calculate exergy destruction of the condenser, you also can calculate exergy destruction of boiler as well as destruction of pump, and if you sum them up you will be getting exergy destruction of the cycle. So, today I am trying to discuss about the exergy destruction of the cycle itself. So, this is in the rate form. So, this is nothing but T naught into S dot out minus S dot in. Right. So, this is what you have studied in thermodynamics, just I am recapitulating. So, the exergy entropy. So, this is nothing but entropy generation. As I told you, more is the entropy generation, essentially due to higher degree of irreversibilities, more will be exergy destruction. So, this entropy generation is essentially due to thermodynamic irreversibility. Okay. So, if you design the system, if you allow the system to operate in such a way that you are going to invite higher degree of thermodynamic irreversibilities. If you invite higher degree of thermodynamic irreversibilities, entropy generation will be more. If you have higher entropy generation, you will be having higher exergy destruction. Higher the exergy destruction, that is degradation of the useful work. So, basically you can understand the efficiency of the cycle will be reduced drastically. So, you know that this exergy destruction, as I told you, that is nothing but a measure of resource degradation, right. So, basically we are trying to get work output from the turbine, but because of this fellow, that is exergy destruction, which is nothing but the entropy generation, which is again nothing but the thermodynamic irreversibilities, we are going to have degradation of the work output, right, resource degradation, that is here we are having work as you know, that is a resource that will be having degradation. Okay. So, now you can write this, this is very short form, that is T naught, just I am writing because you already have studied in thermodynamics, S dot out minus S dot in the rate form. So, that is the flow process, this is not control mass system. So, you are having, you can understand in this process we are having continuous flow, heat addition, heat rejection. So, there is no heat addition, heat rejection over here, but we know that heat transfer due to finite temperature difference, fluid friction, mechanical losses, mixing, all these factors lead to the entropy generation. So, if I try to write for this flow process, so that is m dot, this is out S minus m dot S in plus q out dot by T out minus q dot in by T in. You know that there are multiple, if you have multiple inlet, multiple exit, then this entropy associated with the flow. So, entropy into the flow, I mean that, let us go back to this. So, if we now focus on this particular device, see when steam is entering into the turbine, we are having entropy to the flow. So, entropy into the system, steam is coming out from the system, so this entropy out. If we have, so in this particular device there is no heat addition, no heat rejection, so the entropy transport will be on nothing but the m dot S E S exit minus m dot S in. So, entropy in minus entropy out minus entropy in, right. So, entropy out minus entropy in, that is nothing but the entropy generation. For this case again we will be, in addition to that we will be having heat transfer due to finite temperature difference. Here we will be having heat rejection due to finite temperature difference. Okay. So, this q dot out minus q dot in and this T out and T in are the temperature of the bounding surface through which heat transfer takes place. So, I am writing these are the temperature of the surface through which heat transfer takes place, okay. And these are the entropy associated with the entropy transfer into the system and entropy out from the system, okay. So, if we go one step further, that if we try to write per unit mass, so that is per unit mass, and if we consider that there is single entry single exit, okay, and for the steady state steady flow processes, because here we have seen that by applying steady state steady flow energy equation we could find the enthalpy change, that is if I apply steady state steady flow energy equation to the boiler, to the process which is occurring inside the boiler, to the process, I mean steady state steady flow energy equation applied to the turbine, and then we can find out work output, heat transfer, etc. So, similarly if we can apply steady state steady flow energy equation considering so for steady state steady flow processes, okay, exergy destruction per unit mass having single inlet and single exit can be written x destruction. Okay. So, I am writing T naught into S gen, not in the rate form, and that is nothing but T naught S e minus S I, okay, plus Q out by T out minus Q in by T in. So, you can see that we have written all terms in specific form, that is specific quantities we have expressed in the right hand side. So, and also we did not write in the rate form. Okay. So, this is basically exergy destruction. So, now question is, if we try to write this exergy destruction for the cycle, I mean that the steam power cycle. Okay. So, now if it is applied for the cycle, you know that entropy exit minus entropy in, this term will not be there, because it is a cyclic process. So, whatever entropy is exiting, and that is equal to inlet. So, this is for the cyclic process, I am writing for a cyclic process, okay, cycle or cyclic process. Okay. This x dex can be written, this is nothing but T naught. Now, if we have Q out by T out minus Q in by T in, okay, because we really do not know the surfaces, how many surfaces are there through which heat is added to the system, how many surfaces are there through which heat is rejected from the system. So, this is the heat transfer from the system, this is heat transfer into the system. So, since we really do not know how many surfaces are there, so that is why this is written as generic form. Now, I mean for the present case, if we look at for the present case, as we have discussed that this is considered, I mean if I write in different form, this is considered that this surface is insulated. So, there is no heat interaction, only heat exchange takes place in the boiler as well as in the condenser with the working substance, between the working substance and the surroundings. So, heat exchange between the working substance and surroundings takes place only at boiler and condenser. So, this is also not, I mean a device through which heat exchange takes place. So, for this particular cycle, if we try to write the exergy destruction, so I mean if we write, that would be nothing but, so for the present case exergy destruction is nothing but T naught equal to Q out minus T L minus Q in by T H. Okay. So, this exergy destruction, so this is destruction of the useful work. So, this is nothing but destruction of useful work. Okay. So, try to understand now for this particular case, I mean where you are having only one surface through which heat is added to the system, that is Q in divided by T H. So, this is high temperature thermal reservoir and this is low temperature thermal reservoir. So, Q out minus T L, low temperature thermal reservoir. So, this is T L. So, in fact, I can write T condenser. So, you know that if I again write using different color, say this is the color. So, you know this is basically in the condenser and this fellow is in the boiler. Okay. So, basically you can see that this is basically exergy destruction. If we know the exergy destruction, that is destruction of the useful work, we can find out what will be the minimum work obtainable from the system, right. So, knowing the magnitude of this quantity, that is destruction of the useful work, right, we can predict what will be the minimum work that is obtainable from the system, and from there we can quantify the second law efficiency. Okay. So, to summarize today's discussion, you know that we had started discussion using the second law analysis of the thermodynamics steam power cycle, though we wanted to have discussion of the exergy analysis of the turbine, but since as we have discussed that in a steam power cycle, in a steam power plant there are several other components, not only the turbine. So, instead of just having analysis of the exergy analysis, just by having the analysis of exergy destruction only for the turbine, it is better to have the generic expression of exergy destruction for the cycle, because there are many other components in addition to turbine which constitute together to form the to form the steam power cycle. So, you know that steam power plant, and because of all these components it is possible to operate the it is possible to have all the processes in a cyclic manner. So, that is why instead of having only the exergy analysis of the turbine, we have discussed about the exergy analysis or exergy destruction of the power cycle itself, and we have found that for the cyclic process where the SC minus SI, that is not equal to, that is not there, we can write destruction of available work is nothing but Q out by TL and Q in by TH, this ratio of these two quantities. So, you can see that that is what we have discussed in the last class, that if we can reduce the finite heat transfer due to finite temperature difference inside the condenser, perhaps we can reduce the exergy destruction, right. So, if we reduce the TL, the surface through which heat is rejected to the coolant inside the in the condenser, also if we reduce the Q out, that is amount of heat that will be rejected to the coolant in the condenser, we can reduce the exergy destruction, and if we can reduce the exergy destruction, that will eventually ensure the higher efficiency of the plant. So, with this I stop here today, and in the next class I will be discussing we shall be solving a few numerical problems from the power cycles. Okay. Thank you.